In this video, we're going to be talking about calculus in motion. When we studied displacement time graphs, we investigated the gradient. If we calculate the gradient here, we look at the vertical, we have the change of displacement on the y or the displacement axis, and horizontally we've got the change of time. If we throw this into our gradient formula, we get the change of displacement over time, which of course is the formula for velocity. So we were able to generalize that the gradient of a displacement time graph gave us the velocity. We can generalize this even further. So let's say instead of a graph of straight lines, we have a displacement time graph made using an equation, something like this here. We can find the gradient of this curve by using differentiation. By differentiating this displacement expression, we'll be able to get another expression for our velocity. Something that you'll see written is ds dt, which is the change of displacement over time, which in this case is going to give us velocity. Similarly, we looked at velocity time graphs too, and we looked at their gradient. Vertically, that's the change of velocity, and horizontally, that's the change of time. And if I throw that into the gradient formula, I get the change of velocity over the change of time, which of course is the formula for acceleration. So I can use that idea again. I can say that if I differentiate velocity, I will get an acceleration equation, and I can write dv, differential of v, with respect to time is acceleration. So putting that all together, if I start with displacement and I differentiate it, I get velocity. If I differentiate that, I get acceleration. And of course, I can go backwards and I can do the opposite process to differentiation, which is integration, and that will allow me to get from acceleration to velocity, or from velocity to displacement. Let's have a look at an example. The displacement of an object at time t seconds is given by 2t squared take away 3t plus 4. We're going to try and find the expression for the velocity and an expression for the acceleration. So to find the velocity, we're going to differentiate once, get 4t minus 3, and if we differentiate this expression, we're going to be able to get our acceleration out, which in this instance is just 4. We can also integrate an acceleration equation to get a velocity, and again to get displacement. However, when we integrate, we need to remember the plus c. In these questions, there's going to be some written information that will help us find the value of these constants. So here's the example that we had just now. We differentiated s twice, once to get the velocity, once to get the acceleration. Let's imagine we had this situation where we knew the acceleration, but we wanted to get back to where we started. If I integrate 4, I'll go back to 4t plus c, but that plus 3 element has now vanished. So I'd need to know some information about the initial velocity or the velocity at a certain point in order to find it again. The initial velocities or the initial displacements are things that we're often told, and these are the values of v and s when t is 0. Something that we'll often do is substitute in t is 0 into the velocity or displacement equations. Here's an example. The acceleration of an object is given by 6t take away 8. The initial velocity of the object is 5 meters per second, and the object has a displacement from a fixed point O of 2 meters when t is 1. We're going to try and find an expression for the velocity and an expression for the displacement. So I can get the velocity by integrating acceleration. If I integrate 6t minus 8, I'm going to get 3t squared take away 8t plus a constant. To find this constant, I look at the information about the initial velocity. If the initial velocity is 5 meters per second, this tells me that v is 5 when t is 0. I can substitute this information into my equation. I can replace v and t so that the c is the only variable left. Notice that these terms are just going to cancel, and I'm going to have 5 equals c. And therefore, I can write my velocity as 3t squared take away 8t plus 5. If I repeat the process one more time, I'll be able to get the displacement. We're going to integrate once more. So in this instance, if I integrate 3t squared, take away 8t plus 5, I'm going to get t cubed, take away 4t squared, 5t plus another constant. And this time I'm going to look at the information about the displacement. It tells me that I'm 2 meters away from my fixed point when t is 1. So I can replace s with 2 and t with 1. I'll sub them in once again. And if I tidy up this right-hand side a little bit, we should eventually end up with 2 equals 2 plus c. And that, of course, implies that my constant in this instance is going to work out as 0. So I can plug that 0 back into my displacement formula, and I can just ignore this bit at the end. Here's my displacement equation.